Welcome to this explainer. It's pretty incredible when you think about it, how a loose, totally unpredictable pile of chemical dust actually transforms into that perfectly formed, ultra-reliable pill right there in your medicine cabinet. Today, we're taking a documentary-style journey through the exact unit operations of pharmaceutical solid dosage manufacturing. We're going to track that highly engineered path, step by step, literally from raw powder all the way to a finished tablet.
Here's our manufacturing arc for today: an overview, core granulation methods, granulation equipment, advanced granulation, tablet compression, and finally, coding and processing challenges. Let's dive right in.
Section 1. Tablet Manufacturing Overview. The GMP Process Flow.
All right, let's start with a wide, cinematic establishing shot of the complete good manufacturing practice process flow. Watch how the raw excipients and active pharmaceutical ingredients, or APIs, move in this incredibly precise sequence. Starting right from initial dispensing, they flow directly into dry blending, undergo granulation to build some actual structural integrity, and head straight into tablet compression before hitting those final dedusting, coating, and packaging stages.
Moving to Section 2. Core Granulation Methods. Engineering Agglomeration.
So why is granulation an absolute manufacturing necessity? Well, it's because tablet molds in a press are actually filled by volume, not by weight. If you try to just press raw, airy powder, the flow would be wildly unpredictable. You'd get completely inconsistent dosing, which is a massive no-go in pharma. So we have to use a chemical binder to basically clump that dry powder together. We're transforming primary powders into flowable, dense granules that will press perfectly and predictably every single time.
Now, this granulation process diverges into two core pathways, and it's based purely on the physical limits of your raw material. For stable materials, we're using wet granulation, introducing aqueous or non-aqueous fluids to bind the powder. But what if a product is super sensitive to moisture or heat? In that case, we bypass liquids entirely and rely on dry granulation to protect those delicate active ingredients from degrading.
Within that dry granulation pathway, primary particles are actually crushed together under extreme mechanical pressure without a single drop of liquid. You can do this by slugging, which means producing a large, heavy, temporary slug in a heavy-duty tablet press. Or, alternatively, you can use a roller compactor to continuously squeeze the powder into solid sheets. Those sheets are then carefully milled back down to the exact right granule size.
Section 3. Key Granulation Equipment, Precision and Scale.
Let's take a macro look at the specialized stainless steel equipment driving this at an industrial scale. Looking at this cross-section of a roller compactor in action, you can clearly see the twin horizontal auger feed screws actively driving the raw material forward. Right beneath those, a vacuum deaeration system strategically uses sintered plates to literally suck the trapped air right out of the powder just before it hits those massive counter-rotating compression rolls. This ensures a beautifully solid continuous sheet. Now, if we pivot to wet granulation, the secret sauce to the whole physical transformation is the adhesive binder. Chemicals like povidone or hypermellose are dissolved in volatile, non-toxic solvents to act as a kind of liquid glue. Povidone, for example, is incredibly versatile. You can use it at about 2 to 10% with water, hydroalcoholic, or neat polar organic solvents, and it absolutely guarantees seriously strong particle adhesion once that mixture dries.
Over in a fluid bed granulator, the granulation and drying processes actually happen seamlessly and simultaneously. The raw powder blend gets charged into the main chamber, and then a powerful upward blast of air fluidizes it, basically suspending it midair. While the powder is dynamically floating, binder droplets rain down from targeted nozzles, instantly clumping the particles. Hot air is continuously drying the sweat mask midair until uniform, perfectly sized granules just drop out, ready for discharging.
Section 4. Advanced Granulation Techniques, Modifying the Mechanism.
Beyond those traditional methods, the industry leverages some pretty advanced techniques. At the microscopic scale, we can actually watch this physical transition happen. Precursor molecules chemically interact to form tiny nuclei, which then steadily grow into fully consolidated, robust agglomerates. Looking at this scanning electron microscope imagery, it's like a macro slow-motion film. You can actually see base ingredients like lactose and microcrystalline cellulose growing step by step into complex, highly structured granules. One of these highly advanced methods is melt granulation. Instead of relying on a liquid solvent that you eventually have to evaporate off, this technique uses pure thermal energy. We melt binders like polyethylene glycol at precise temperatures right between 50 and 80 degrees Celsius. As the active mixture cools down, the binder solidifies. It's a brilliant, elegant solution because it bypasses the need for a drying phase entirely, making it absolutely perfect for those moisture-sensitive APIs.
Modifying exactly how we deliver that binder can also radically alter the final physics of the granule. For example, using pure steam instead of liquid water creates highly porous, spherical granules that basically dissolve instantly upon consumption. On the flip side, injecting the binder as an expanded foam drastically improves the liquid's surface area coverage across the whole powder bed, which completely avoids the risk of over-wetting your material.
Section 5. Tablet compression, the compaction cycle and tooling.
Okay, so with our granules perfectly engineered and optimized, we leave the granulation suites and enter the compression phase to actually forge our final solid dosage forms. But before we press those granules, we should definitely note an alternative path: direct compression. If your raw powder mixture inherently has exceptional flow and compressibility right out of the barrel, you can just skip granulation entirely. It's a super streamlined process involving just two operations: dry powder mixing and immediate tableting.
At the heart of the tableting machine is this highly precise, engineered tooling interaction. It all comes down to the perfect, synchronized alignment of a stainless steel upper punch, a hidden lower punch beneath it, and the exact dimensional volume of the die cavity holding the powder right in between them.
This continuous compaction cycle happens in a high-speed blur. It starts with the filling stage. Here, gravity pulls the powder directly from the feed hopper straight into the open die. And that die is perfectly sealed at the bottom by the lower punch to capture the exact, precise volumetric dose we need.
Immediately following the filling stage is compression. The upper punch descends smoothly, but with massive force, right into the die cavity. It's applying immense mechanical pressure to crush, bind, and literally lock those granules together until a highly stable, compact tablet is born.
Finally, we hit the ejection stage. The upper punch rapidly retracts upward, and the lower punch pushes up until it sits perfectly flush with the die table surface. Then a mechanical sweep arm swiftly pushes the newly finished tablet right out of the compression zone. And this entire, flawless cycle instantly repeats itself, thousands of times a minute.
Section 6. Coding and processing challenges. Final form complexities.
So, while direct compression sounds incredibly efficient on paper, in reality, it introduces some pretty severe processing bottlenecks. It absolutely requires large particles just to flow properly into the die. Plus, it often demands very expensive, highly engineered fillers, like Avicel, just to work at all. It severely struggles to uniformly distribute low-dose drugs throughout the blend, and it completely fails at handling high-dose, bulky drugs like magnesium hydroxide. It even struggles to evenly distribute deep color pigments without mottling. And then, even after you achieve a perfect compression, applying the final tablet coating for environmental protection and taste masking introduces massive operational complexity and exorbitant specialized equipment costs. Knowing the immense precision, engineering, and pure expense required just to reliably create a single flawless pill, it really leaves us wondering, how will the next generation of pharmaceutical engineering innovate to break these final manufacturing bottlenecks? Thanks for joining me on this explainer. I hope you found it as fascinating as I do. Catch you next.